everyone. So today we are going to kind of take a peek behind the scenes of this integral idea that we've been dancing around. And we already know how to find Riemann sums, which is what this is based on today. And Riemann sums make a really good approximation for what an integral actually is. But the idea is, how can we take a Riemann sum and make it better and better and better and better until it actually gives us the correct area? All right, so that's sort of the method that we're going to use, and I'm going to use a visual to kind of show you how this works. And then really we're just going to take that idea, that process, and express it with some notation. So I think the big picture idea here is going to be really easy for you to grasp. The notation can get a little clunky, so just try not to lose sight of like the big picture when we get all, kind of consumed by all of this scary looking math notation. And then I'm going to show you at the end some of the questions that you'll be asked about this on the AP exam, so that you have an idea of what you'll actually need to do with this notation. And spoiler alert here, it's not much, okay? It's really more a matter of just kind of recognizing what this notation is talking about, rather than actually being able to like use it and create it yourself. So let's talk about that Riemann sum idea here for just a second. So this is a tool that is just going to show us, a calculated Riemann sum, and I don't know why it's not, let me make it full screen here, but it's a calculated Riemann sum, and it's going to show us how this compares to the actual area. So right now I'm looking at the function f of x equals x squared. I divided this into 6 rectangles. This is currently a left Riemann sum. This tool will let me do, a midpoint Riemann sum or a right Riemann sum, but we'll just stick with left for right now. For the process we're talking about today, it actually doesn't matter. And so you can see that if I divide it into these 6 rectangles and find that combined blue area, that area is 6.875. Okay, and this is an integral from 0 to 3. I've kind of defined that too. But we know this is an underestimate of what the actual answer should be, because I have all these blank spaces here, right? These spaces that look kind of like triangles. And so I'm missing out on some of my area by doing this left Riemann sum, okay? And of course I could do a right Riemann sum, but then I have the opposite problem. I have an overestimate on my hands. And if you look at that number, it's 11.375. So that's a little bit higher than what the actual area is. So I know this is too low, and I know this is too high. Okay, let's go back to our left one. And I want you to watch what happens to that number as I increase this n value. N is controlling how many rectangles I have. So as I make more rectangles, you should see that that number is growing and growing and growing. And that's because my space here, that would be my underestimate, is shrinking. These rectangles are able to get closer to the function when I make them skinnier. Okay? And I can make them really, really skinny, okay? So I'm taking this space right now, this from 0 to 3, and I am creating 30 rectangles in there. That means the width of each rectangle is like 0.1, okay? And I can make them skinnier than that. I can make, 60 rectangles. And with 60 rectangles, that would be like 0.05 for my width. And look at how close that is to the actual function. My spaces are really, really shrinking. They're still there. This is still an underestimate. I know my actual area is still bigger than this number, but I could do this forever. I could make my n values larger and larger. On this tool, it maxes me out at 80 rectangles, but you get the idea here, that if I make n larger, I'm getting a better estimate, okay? So this is still an underestimate, but I'm getting closer to what the actual area is. That's a way better estimate than back here, when I had an estimate of, 5 or 6, something like that, okay? Let's look at what happens when I flip over to a right Riemann sum. So this is a right Riemann sum with those 80 rectangles in there. This is an overestimate. These rectangles are still popping up above the function, and you'll notice that this Riemann sum is 9.16, okay? Which is a little higher than what the actual area is. The thing I like about this tool is if I get rid of these rectangles, I can actually find what the true area is here. So if I click actual area, this green area, okay, the actual area should be 9. And so that right Riemann sum, okay, when I take it way back here to just a few rectangles, I can see this area, my Riemann sum is 11.375. It's way above 9. But as I increase n, this number, watch that blue number up at the top, is getting closer and closer to that actual area of 9. Okay, if I flip over and do a left Riemann sum, my area started really small, and then it grew and grew and grew and got closer and closer to that actual area of 9. Okay, and so that's how, like, when your calculator is calculating an integral, this is really what it's doing, is it's doing a Riemann sum with really, really tiny slices, okay, to get as accurate as it possibly can. So let's take a look back at your notes now. And this right here, this sentence in pink is what we were just talking about, is we calculate the area by finding a Riemann sum. We use n subintervals, and then we increase that n value. We make that n value bigger and bigger and bigger until it can't get any bigger, okay? Well, it can always get bigger, that's the idea. So if you think about what that means, is if you're taking n and you're increasing it forever, and then when you make it as big as you think it can possibly go, making it even bigger, what we're really doing is taking that Riemann sum and doing a limit as n approaches infinity. And I'm just going to do this for right now. So I'm taking the Riemann sum, doesn't matter if it's a left or a right, that n value is how many intervals I have, and I want to take the n and run it to infinity, and that limit as I'm approaching infinity is what my actual area is. Okay? Okay, that's the big idea today, all right, is we want to somehow express this mathematically. The hard part actually comes in. This limit as n approaches infinity. This is going to stick with us all the way through the lesson. But now what we really need to do is dive into this thing right here, this Riemann sum, and think about how can we write a Riemann sum in notation, in like fancy math notation. And that's really what the rest of our focus is going to be on today, is how to write a Riemann sum in sort of an official way. Okay, so I've given you just kind of a random function here, and I'm going to just define an integral here. So let's say, and I'm going to use kind of a mix of numbers and then like generic variables, but I'm going to say that we're going to do an area from 0 to, oh, I don't know, let's just say this is going to be 5. Okay. And we are going to find this area with a Riemann sum, and remember that n is going to represent the number of subintervals, okay, that we're working with. So I'm going to just draw some subintervals in here. What we want to do is what you just saw in that visual tool a second ago. We want to make more and more and more subintervals. Like no matter how many I draw, I want to draw more. But for the sake of just drawing it on a picture, I'm just going to draw a few to get us started. So we'll just do like, I might make them a little wider just to give myself some more room to write. So we'll go. Okay, so this is actually going to give me 4 subintervals, 1, 2, 3, 4. But I'm not gonna talk about it like there's 4 there, because I actually want there to be more than 4. I want there to be as many as I could possibly dream up. Okay, and I'm going to just draw this as a right Riemann sum. Again, it doesn't really matter, but I think the visual makes more sense with a right Riemann sum. So for a right Riemann sum, let's see, this rectangle would be kind of anchored here. That's my first rectangle. My second rectangle would be anchored here-ish. My third rectangle would be anchored about here. And then my fourth rectangle would be anchored right there at that 5. Okay, so these are the 4 rectangles that I'm working with in my Riemann sum. Okay, so let's start simple, all right? Let's start with just, we need to find area of a rectangle, okay? And so I'm going to start with area of a rectangle is equal to base times height. So let's talk about the base of one of these rectangles, any one of these rectangles. We need to be able to figure out how long is this length right here. And I am going to assume that I'm working with equal intervals, okay? For the sake of the notation, we're assuming that we're working with equal intervals here. So like if this goes from 0 to 5 and I had 4 subintervals, I could very literally find this length by doing 5 divided by 4, right? And I would find that each of these is 1.25, okay? But again, I don't want to use the number 4. I want to use n so that I can make my n get larger and larger and larger. Okay? So if I had 10 subintervals, I would do 5 divided by 10 to find out how wide each one should be. If I had 20 subintervals, I would do 5 divided by 20. And so in notation, I am just going to say that the width of one of my subintervals is 5 divided by n. And then this would be 5 divided by n. This would be 5 divided by n. And then this width right here would be 5 divided by n. So when I'm writing out my area of my triangle, I'm sorry, of my rectangle, my base is 5 over n. Okay? That's the easy part. The next part gets a little bit harder. Okay? The height of each of my rectangles. So the heights of my rectangles come from these right endpoints. Okay? Oh, somehow I don't have my, this should be drawn right here. There we go, on the function. Okay, here and here. These values are what it's going to determine my heights. And these come from the function. So I'm going to find these by doing f of something. I might run out of space there. I might have to draw arrows from up above. Okay. The question is, what do we call this number right here? Okay. And again, we could do this like with actual numbers, but I'm trying to pretend like n could be anything. Okay. So just what would I call this right here? Well, if I started at 0 and I moved over by 5 over n, then this value must just be 5 over n. Okay. And then that means that this comes from f of 5 over n. Okay, my height there is 5 over n. F of 5 over n, I should say. Okay, so then what is this value? Well, if you think about this, this is like I have moved by 5 over n twice. Okay, right? I've moved by that length twice. I've moved it once and then I've moved it a second time. So this would really be, I mean, I could call this like 10 over n. Okay, but I'm going to write that a slightly different way when I write it up here. I'm going to call this point here f of 5 over n times 2. Okay, and just for consistency, I'm going to go back here and say this was 5 over n times 1. And this is 5 over n times 2. So this would be f of 5 over n times 2. So then what's this guy? Well, if I'm just counting by 5 over n, I could call this 15 over n, which is the same thing as saying 5 over n times 3. And then this last point would be f of 5 over n times 4. And I know you're screaming at me like, wait a second, we know what that is. That's 5, right? Well, think about this. If I was literally using 4 subintervals and I put 4 here, I would have 5 over 4 times 4. And that would just leave me with 5. So that's exactly what this is. This is f of 5. Okay? But I wrote it this way because remember, what we want to be able to do is generalize down here when I write my height. Okay, I want to be able to talk about any rectangle I draw. It doesn't matter, you know, how many rectangles I've drawn. I want to be able to pick any one of them and say what's the height. Okay, and so I would say that my height is f of 5 over n times k. And k, just to throw another letter in the mix, k is this number right here. Okay, so whichever rectangle I'm standing at, if I draw 100 rectangles and I'm standing at the 12th one, okay, I could find that height by doing 5 over n times 12 and then plugging that into whatever my function is. So f of the 5 over n times 12, because that's how far I would have to move over to the right. So this right here, this is my area. Okay, this is my area function. Now, this is where I'm going to jump back into some Algebra 2 notation. What I want to do then is take this area and I want to add them all up. I want to find all of these areas and add them together. And hopefully this notation looks a little bit familiar to you. But in Algebra 2 last year, we learned that we can say we're going to add something up using this sigma notation. Okay, if you remember this guy, this means I'm going to take like a list of numbers and add them together. And this list is being generated based on this k number. So I want to take k and make it run from 1. Okay, so k, when k equals 1, that's talking about my first rectangle. My last rectangle would be when k equals whatever my n value is. My last rectangle is always going to come from, that's my nth rectangle. If I make 100 rectangles, then this would be 5 over n times 100. Okay, so this needs to run from k equals 1 up to whatever n happens to be. So in this case, if you're looking at the picture that I have drawn here, I have 4 rectangles drawn. So k is from 1 to 4. 1, 2, 3, 4. Okay, so these are the k numbers that I'm talking about. And then I'm going to say what I'm taking the sum of are these areas. So I'm going to say of 5 over n times f of, and I'm going to rewrite this a slightly different way just because it's how you'll usually see it in these problems. I'm just going to put the k up with the 5. Okay. And so what this is saying is find the area of a rectangle, okay, of all of the individual rectangles, because that's what k is representing. And this is saying add them all up, okay? And then we're going to tack on that piece that we talked about up here, where we say, now what I want to do is make that n value as large as I possibly can. So what I'm going to throw in front of this is a limit as n approaches infinity. And symbolically, this right here is how I would write this area. Okay, the integral from 0 to 5. So I would say something like, you know, the integral from 0 to 5 of f of x is equal to this limit right here. Okay, that's a lot to take in, and there's one more tiny piece that I want to talk about. But again, that's where this notation is coming from. This right here is the base and the height. If you want to jot this in, this is the base of my rectangles, this is the height of my rectangles. And the k is just talking about which rectangle are you on. This is rectangle number 1, this is number 2, this is number 3, this is number 4. Okay, so the k represents which rectangle you're talking about. And I want to just say here that I want to take all of the rectangles. So I want to start from the first rectangle and go to the last rectangle. Find all of those areas and add them up. That's what this sigma is talking about. And then I want to keep doing that process, but I want to keep making n larger and larger and larger and larger. And that's what this formula represents. Okay. Tiny bump in the road here. Okay, if all of that makes sense to you, great. If it doesn't, now might be a good time to pause and just kind of digest, or rewind the video and maybe rewatch parts of it if parts of it don't make sense. I'm going to add one little snag here, because I did something very convenient with this example. I started us right at 0. So when I started us right at 0, I was able to just say this first jump would just be like, this is 5 over n, because I went from 0 and I moved by 5 over n. But let's say now that I wanted to do an integral from, I'm going to just make it the same width, so I'm going to say this is 10. But let's say I wanted to know this area from 5 to 10. Let's say I wanted to do this integral. My process is going to be the same. So my width of all of these intervals, no matter how many I draw, I'm still going to say this total distance is 5. So this width is still 5 divided by n. Okay, these are 5 divided by n, 5 divided by n. So if I were to go write this limit notation, I would start out with limit as n approaches infinity. And I guess I should start by saying the integral I'm trying to calculate is from 5 to 10. F of x dx. I'm taking a limit as n goes to infinity. I'm still making my k value run from 1 to n, because again, that's talking about the rectangles. I'm drawing rectangles in here. Okay, oh, I guess I should have tried to hit my marks, but that's okay. The width of my rectangle, so this part's always going to be the same. This is never going to change on you, okay? The base of my rectangle is still going to be this width of 5 divided by n, okay? The problem is going to come in like, how do I name this right here? Because I can't just say it's 5 over n, because that would be like starting from 0 and moving by 5 over n. So what I need to do is I need to start at 5, okay? So when I go to name this point, which again, let's pretend like I actually drew my line where it was supposed to go. When I'm trying to find this height, and I want to figure out what is this, this would be starting at 5 and moving by 5 over n. So it would be 5 plus 5 over n, and this is the first rectangle, so I'm only moving by that number once. When I go to do my second rectangle, which would be right here, okay, this would be 5 plus 2 5 over n's. So I started at 5 and jumped by 5 over n twice. So this value would be f of 5 plus 5 over n times 2. So the thing that has to change here is inside this f value, I'm going to take that 5 as my starting value. I'm going to take this number and just stick it in here. 5 plus 5k over n. Okay. We're going to take that and write it a little more generalized here in just a second. You're probably looking at it already and going, wow, that is way too generalized already, and I'm with you. But I just want to get rid of some of these like specific numbers that are in here because of like the picture that I drew. What you're ultimately going to have to do with this, and I think in the next example I do have you actually writing one from scratch, but the way this is going to work on the AP exam is it's going to be questions where they give you something like this that's already written, and you just have to be able to kind of translate back into an integral. And the pieces you want to look for is, for example, this 5, that's talking about how wide is your interval, right? How wide am I going along the x-axis, okay? So in both of these situations, the width of my interval was 5 units. That's why this is 5 over n, okay? And then this thing here, anywhere you see that 5k over n, that's just kind of a stand-in for your x value. Okay, so this thing, and this is always going to look like this, but with a k in it, that's always just your x. Okay, that's just telling you like where are you determining these x values from. And then if you do have a number that's in here as like an addition, okay, inside that function like that, that's telling you your starting value. So this one didn't have one because my starting value was 0. This one would have a 5 sitting here because my interval starts at 5. Okay, and so those are kind of the pieces that you're going to look for. But let's head back up here to where it just says summation notation, and we're going to write down kind of our final draft version of this. But we're going to say that if we're trying to find an integral from a to b of f of x dx, we're going to take the limit as n approaches infinity, and that's the same idea that we started with, right? It's a limit as n approaches infinity of the sum, because I'm doing a Riemann sum, so the sum, and this is always going to be k equals 1 up to n. That part's never going to change on you. We're going to start with the width of the interval, okay, divided by n. Remember, n is your number of subintervals. So if I'm doing this generally between b and a, the width of my interval would be b minus a over n. Okay, so this would be like my 5 from down below. And then I'm multiplying that by f of, and I'm going to start at a and then jump by this number, the b minus a over n times whatever k is. Okay, So what I have written there in kind of that burgundy color there in the middle, this is sort of your formula, okay? And again, it probably won't look this messy because there will be an actual number in here for b minus a. There will be an actual number in here for a. But what you want to understand is that this b minus a is your width of your interval, and this a is where your interval is going to start, okay, when you write your integral notation. Everything else is just scary looking notation, okay? And then we're also going to talk about, like, if we actually have a function to work with, what that's going to look like.